Okay, problem 6. We have 1 plus sine of rho times 1 plus sine of negative rho equals cosine squared of rho. Okay, so first, I see I can use an even odd identity right here. So that makes this second parentheses 1 minus sine of rho. Then we have 1 plus sine of rho equals cosine squared of rho. So now I'm going to distribute. And so I get 1 minus sine squared of rho equals cosine squared of rho. And then I notice that this here is really a Pythagorean identity. So if you recall, I have cosine squared of u plus sine squared of u equals 1. And then if I subtract sine squared of u from both sides, I get cosine squared of u equals 1 minus sine squared of u. Okay? So this here is really cosine squared of rho. So I have the same thing on both sides of the equation, so that's proven. So QED, it has been proven. Okay, now we look at number 7. And I see right here and here I have some even odd identities again. They're also called negative identities. Okay, so cosine of negative u, or mu, that's a mu, is cosine of mu. And then sine of negative mu is negative sine of mu, so I get 1 minus sine of mu equals secant of mu plus tangent of mu. Okay, so these are two separate expressions here, and I want to work on this side only. So what I'm going to do is I'd like to make this two terms. So what I'm going to do is I'm going to multiply by 1 plus sine of mu over 1 plus sine of mu. Okay, and put parentheses around that. So I get cosine of mu times 1 plus sine of mu. Then when I distribute this, so we call that multiplied by the conjugate, was that step. Now I'm going to distribute, distributive property, right? So I get 1 minus sine squared of mu. That equals secant of mu plus tangent of mu. Okay, now 1 minus sine squared. You better start recognizing that. That's a Pythagorean identity. So 1 minus sine squared, that's cosine squared there in the denominator. So then I have cosine mu plus 1 plus sine of mu equals secant of mu plus tangent of mu. And that's the Greek letter mu, which is written like that. Mu or mu. Alright, so now I see I have cosine squared, so it's cosine times cosine, so I'm going to simplify, or I could say reduce. So now I have 1 plus sine of mu over cosine of mu equals secant of mu plus tangent of mu. Alright, so now I'm going to divide into two fractions, okay? So separate fraction. So it's 1 over cosine of mu plus sine of mu over cosine of mu equals secant of mu plus tangent of mu. So if I use my reciprocal, this becomes secant of mu, which is that. Then if I use, let's say, ampersand and quotient identity, that makes sine over cosine tangent. So I got what I want, QED. Okay, a couple more. See how that's one term, secant times cosecant? I'm going to keep this one. I'm going to keep this a term. So I'm going to use secant squared. I'm going to say that's really reciprocal identity. And tangent, I'm going to say and a quotient identity. Okay, so that's 1 over cosine squared of epsilon over sine of epsilon over cosine of epsilon equals secant of epsilon cosecant of epsilon. I'm going to make this fraction bar longer because it's a fraction divided by a fraction, right? It's a complex rational expression. So I'm going to divide fractions or rational expressions, okay? So when you divide, you multiply by the reciprocal. And that's equal to secant times cosecant of epsilon. Now, cosecant squared on the bottom, cosine of epsilon in the numerator. So one of those cosines crosses out, reduces. So I have 1 over cosine times 1 over sine. So just simplify or reduce equals secant of epsilon times cosecant of epsilon. So 1 over cosine, that's secant of epsilon. So 1 over sine, that's cosecant of epsilon. So that's just going to be reciprocal identities. That's been proven, QED. Looks like there's going to be a part 3.